The Louis Burke Frumkes Center for Writing and Culture at Hunter College presents 10 years of best-selling authors and great thinkers.
Is there life on Mars, Venus, the new planets that were discovered in the last few weeks, or any place else in the universe? We all want to know, and if there is, we want to know what it is like. The perfect person to answer these questions is David Grinspoon. David not only comes from another planet, isn't that so, David? Yes.
From a planet.
Yeah, but he is a fabled astrobiologist and senior scientist at the Planetary Science Institute. He was also the protege and friend of Carl Sagan, the great scientist and author who popularized interest in the cosmos and the possibility of life on other worlds. David studies planetary geology and geophysics, planetary atmospheres. So, for example, you might ask him if there is methane on Titan, and if so, could we have methane-based life there? You don't have to ask that, but that's an interesting question. He studies exobiology, does work for NASA, the European Space Agency's Venus Express mission, and the Mars Science Laboratory. He is the lead scientist for outreach of the Titan astrobiology lead team and has written and performed several original planetarium shows. Suffice that he writes award-winning books, such as Earth in Human Hands, on planetary science and on astrobiology. He lectures widely on these subjects and has participated in numerous popular TV shows and radio productions. In fact, his scientific credits and awards are so numerous and impressive that they just might reach from here to the moon, so to speak. It gives me great pleasure this evening to welcome David Grinspoon here as one of our great thinkers at Hunter College to speak to you about the wonders of space, the possibility of life on other worlds, the future of life on this world, and his extraordinary contributions to our current knowledge in that field. David?
Thank you for that very kind introduction. I started the project that ended up as this book, Earth in Human Hands, when 4 years ago I was honored to be selected as the inaugural chair of astrobiology at the Library of Congress in Washington. It was a new position, and they wanted people to propose projects that were on the intersection between astrobiology and wider human concerns, between the science of astrobiology and the humanities. So I proposed a project to study the astrobiology of the Anthropocene epoch, which is the word that people are now using to describe the idea that we have entered a new geological phase of Earth history that people are calling the Anthropocene, meaning time of humanity. And I decided that I wanted to study that concept through the lens of astrobiology. So this is by way of answering the question, why would an astrobiologist, somebody whose profession is thinking about other planets and life elsewhere, write a book about the human presence on Earth? And I want to start right off by reading you a little bit from the introduction of this book, where I attempt to answer that question. This is from the very beginning of the book, A Planetary Perspective on the Human Predicament. Gazing over the countless fluctuations and transformations in Earth's multi-billion-year history, I am struck by the unique strangeness of the present moment. We suddenly find ourselves sort of running a planet. We suddenly find ourselves sort of running a planet, a role we never anticipated or sought, without knowing how it should be done. We're at the controls, but we're not in control. This book is my view of how we got into this situation and where that leaves us now. A child of the space age, I grew up captivated by the romance of planetary exploration. My timing was right to become a NASA research scientist working in the new field of astrobiology, the scientific study of life in the universe. My participation in the spacecraft exploration of other planets has informed my view of our presence on this one. In these pages, I'll describe how we humans fit into the long-term story of Earth and how I believe this knowledge can help us to navigate our current time of environmental stress and uncertainty about the future. Although climate change is the most obvious, it is only one of a large number of interconnected ways in which we have suddenly begun to modify the planet we inhabit. The scientific community is now converging on the idea that we have entered a new phase or epoch of Earth history, one in which the net activity of humans has become a powerful agent of geological change, equal to the other great forces of nature that build mountains and shape continents and species. The proposed name for this new epoch is the Anthropocene, or the Age of Humanity. This concept challenges us to look at ourselves in the mirror of deep time, measured not just in decades or centuries, or even in millennia, but over hundreds of millions and billions of years. We are witnessing and manifesting something unprecedented and still completely unpredictable: the advent of self-aware geological change. As an astrobiologist, I study the possible evolutionary relationships between life and the planets that may host it. I see the Anthropocene as a tricky new step in the long, intricate dance between Earth and its biosphere that has been going on for 4 billion years. There are those who object to the name Anthropocene as being too self-aggrandizing and serving a destructive, human-centered viewpoint. But this epoch is well named because it represents a recognizable turning point in Earth history brought about by one species, Anthro. And our growing acknowledgement of this inflection can be a turning point in our ability to respond to the changes we've set in motion. I believe that more than the extreme and undeniable physical changes to the planet being caused by human influence, it is this dawning self-recognition that is really fundamentally different and ultimately promising about the Anthropocene. Many species have changed the planet to the benefit or detriment of others, but there has never before been a geological force aware of its own influence. And then a little bit further down in the intro, I talk about the planetary perspective. It may seem circuitous to begin a book about the human role on Earth by talking about the exploration of other planets. I will try to make the case, however, that looking homeward from the vantages we've gained through our interplanetary journeys gives us valuable perspective for navigating the planetary scale changes we are now facing and causing. We need to learn all that we can about how planets work so we can make the transition from inadvertently messing with Earth to thoughtfully, artfully, and constructively engaging with its great systems. The planetary perspective allows us to step away from the noise of the immediate present, to see ourselves from a distance, in time lapse. When we do so, what we see is not just a problem facing our civilization, but an entirely new evolutionary stage in the development of life. In seeing ourselves as a geological process, we also see the planet entering a phase where cognitive processes are becoming a major agent of global change. Earth's biosphere gave birth to these thought processes, which are now in turn feeding back and reshaping its changing planetary cycles. A planet with brains? Fancy that. Not only brains, but limbs with which to manipulate and build tools. We are just beginning to come to grips with this strange new development. Like an infant staring at its hands, we are becoming aware of our powers, but have not yet gained control over them. And then I have one more snippet from the beginning of the book I want to read to you. The planetary perspective provides a kind of out-of-body experience for us, hovering in orbit and watching ourselves sleepwalk through a slow disaster of our own making. Now, can this experience help us to shake ourselves awake? For virtually all its history, Earth has evolved without us, and we have always seen ourselves as autonomous actors on a passive planetary backdrop. But now we are beginning to see that our futures, those of humanity and of planet Earth, are tightly conjoined. If human civilization is to persist and thrive, we will need a completely different view of our planet and of ourselves, in which we acknowledge both our deep dependence and our increasing influence. We need visions of a future in which we have applied our infinite creativity to the task of living on a finite world, where we have embraced our role, become comfortable and proficient as planet shapers, and learn to use our technological skills to enhance the survival prospects not just of humanity, but of all life on Earth. My name for this vision is Terra Sapiens, or Wise Earth. A recent scientific breakthrough enriches this story, the exoplanet revolution. As we long suspected and have now confirmed, this universe is full of planets orbiting nearly every star. It is now very close to inconceivable that we could be the only life and only technological intelligence in the universe. An interplanetary perspective on Earth's current dilemmas incites us to wonder whether parallel dramas may have unfolded on distant worlds. Do other planets also grow inventive brains that end up causing themselves problems? Do other species develop technology and build civilizations that create dangerous instabilities on their planets? How do they cope? Do planetary biospheres become self-aware? The Anthropocene leads us to a new way of looking at SETI, the search for extraterrestrial intelligence, which in turn illuminates changing notions about ourselves, how we fit into our planet, and what kind of future we dare imagine. 100 million years from now, what will our time have been? A brief climate spasm that Earth shrugged off and largely forgot, leaving a thin layer infused with bizarre plastic objects? Or the beginning of a lasting new phase when the biosphere finally woke up and adjusted its grip on the planet. So that's all from the beginning of the book, where I'm sort of framing my approach and why an astrobiologist would try to look at the phenomenon of humanity on Earth as a geological process. And then the first part of the book is called Listening to the Planets. And it's where I describe planetary exploration that started in the early 1960s, but with a focus on what we've learned about our own planet from exploring the rest of the solar system. And starting in, really in 1961, we gained the ability to launch spacecraft to other worlds, and this obviously taught us a great deal about some of these neighboring planets. And in a lot of my scientific work, I've worked on this, on the comparison between Venus, Earth, and Mars, which is just, they may form an interesting trio because there are two neighboring planets and they're both somewhat Earth-like, but they've diverged in interesting ways. And the comparative planetology of these worlds tells us a lot about how planets work in general, but it also reflects back and has led to a number of deep insights about our own planet that we would not have had we not started exploring other planets, not just interplanetary exploration, but also important in this is the existence of a growing network of Earth-observing satellites, so we can observe our own planet whole and from a distance. And some of these insights include the theory of plate tectonics, which at the beginning of the space age was a fringe idea and is now understood as the central idea of Earth science that connects the way we understand disparate phenomena on the Earth. And that's basically the idea that Earth's surface is split into about a dozen rigid plates that slide around with respect to one another, and when they crash into each other or slide under or pull apart from one another, that's what causes most of the geological activity on our planet. But it goes deeper than just the surface. It's also an idea about the internal convection, the deep motions inside the planet, and the motions of those plates ride around on those deeper currents. And it's also the way now we understand our atmosphere and our climate and all these cycles, the carbon cycle, the nitrogen cycle, the oxygen cycle, they're all connected with this churning of the earth and motion of the earth in the interior and the exterior. So it's sort of the grand unified theory of earth science. And two other big insights about Earth that came out of the space age. One is the fact that we're much more closely connected to the rest of the solar system in terms of planetary history than we once knew. You look at the moon, the surface of the moon, and what do you see? You see craters everywhere because the moon has been getting hit over time by the stuff, that's the random stray stuff in space. Well, Earth has been in the same region of the solar system throughout all its history, so why isn't Earth full of holes? Well, it turns out that Earth has been also getting hit throughout its whole history by objects from space, but because Earth is so active with that plate tectonics and geological and meteorological activity, erosion, and even the life itself, the biology, Earth's surface is constantly remaking itself and sort of repaving those potholes that are just laid bare on a dead surface like the moon. But when we study the history a little more carefully, we see that Earth has been hit and influenced over and over again from the outside. Most famously, the big impact that struck Yucatan, Mexico 65 million years ago and caused the mass extinction of not just the dinosaurs, famously, but 75% of all other species at that time. That's the one we hear about the most, but in fact Earth has been hit many times and will be again if nobody does anything about it. And there are other important connections with the rest of the solar system too. It turns out that our climate over the long term is controlled by this cycle that we call the Milankovitch cycle of ice ages and hothouse epochs that follows a convoluted rhythm that is driven by the orbit of Jupiter and to some extent Saturn as well. These planetary influences over the long run just slightly tweak Earth's orbit and its spin in ways that control the long-term climate cycles of the planet. Again, something we didn't know until we started exploring recently. Sadly, the guy that figured this out, Milankovitch, he did the math about this when he was a prisoner of war in World War I, scrawling it on the walls of his prison cell, and he went to his grave with everybody thinking he was a crackpot. And then in the 1970s, when we started understanding climate history because of drill cores, we saw the pattern, and it turned out he was exactly right, what he had predicted, but he never knew that in his lifetime. Anyway, so now we know that Earth's climate is also connected with the orbits of the other planets in the long run, and even human evolution, it turns out, has been driven by these climate cycles, which are ultimately driven by the planets. It turns out that a lot of the major big steps in our becoming modern humans, the evolutionary innovations that we think of when we think of what it takes to be human, upright walking, large brain sizes, domestication of fire, various social and technological abilities and cultural abilities. A lot of those are correlated in evolutionary history with times of climate change and came about as responses to climate change in Africa that were driven by these planetary cycles. So there's some very interesting connections with both our planetary history and our species history that go beyond our planet, that we didn't know about this till we started exploring. When we look at this trio of planets, Venus, Earth, and Mars, what we've learned about their histories is that they started off all very similar. Venus and Mars seem to have both had much more Earth-like conditions when they were young infant planets. All three probably had liquid water oceans and geologically active surfaces and organic matter. All the conditions we associate with the requirements for the origin of life probably existed on all three of these planets. But if there was an origin of life on Venus and Mars, it didn't stick. On Earth, it did. The three planets started out similar, but then each one went through some kind of a catastrophic transition. On Venus, there was a runaway greenhouse. It became very hot, the water boiled off, and it's today left as a desiccated oven world. On Mars, the gravity was too low. It just couldn't hold on to its atmosphere very long. The geology died out. The atmosphere mostly escaped into space. The oceans dissipated, and Mars today is a frozen desert. And Earth, early on, went through its own kind of catastrophic transition. Namely, Earth came to life. There was an origin of life, and life took over and radically transformed the planet. And the more we study Earth, especially in comparison with its lifeless neighbors, the more we realize the deep extent to which life has completely remade our planet. Not just in the obvious ways like the oxygen content of the atmosphere and the composition of the ocean and the green continents, but in all kinds of other ways too. Earth has been remade by life. The rocks themselves, more than 2/3 of the minerals on Earth are byproducts of biology in one way or another. And now it turns out even those deep motions in the interior of Earth, in those realms that you think of much deeper than the biosphere could extend, are probably also influenced by life in a way, because life alters the material properties of the rocks themselves through its chemical influence, through those great chemical cycles that permeate the planet. So life has really got Earth in its grips. And looked at in this comparative planetology way, you can see that early on in its history, there was a branching point. And when Earth became alive, in a sense, it went down a fundamentally different path than those of these other planets. And I describe it that way as sort of a setup, because then the next part of the book, I start talking about human influence. And I suggest that what is happening to the planet now, in a certain sense, is another branching point, potentially another transition as great as the origin of life itself. The takeover of the planet, or the great influence of the planet by cognitive processes, if that becomes something that is a long-lived stabilizing force on the planet, then that could be a transition as great as the origin of life. And interestingly, when life formed, life may have formed on Venus and Mars, but it did not become a long-term stabilizing influence. But on Earth, it did. It wasn't just that we had an origin of life, but life became a planetary property. And that's an interesting way to think about what's happening on the planet now, that cognitive processes are influencing the planet, but they may or may not become an integral part of the way the planet functions. That depends on what happens with this Anthropocene epoch. So anyways, the next part of the book is where I get into human influence, and the chapter where I sum up the influence of humans from the Earth's point of view. I describe humanity from the Earth's point of view, and that section is called Monkey with the World. And I'm going to read you just a little bit from the beginning of this chapter called Monkey with the World. This is how that chapter begins. It's called Something New. Have you noticed that something strange is happening to Earth? Take a good long look at this world, a dazzling blue orb festooned with spiraling clouds, spinning through star-flecked darkness. Dayside glinting in slowly brightening sun, winter white pulsing between north and south as Earth ambles through its orbit. Now, imagine you are a very patient alien regarding Earth over the eons. If you've been watching carefully for, say, the last several billion years, You've seen a lot happen. The brown continents drifting around the oceanic globe, coalescing and breaking apart, animated pieces in a morphing spherical puzzle. The polar caps growing and shrinking, advancing and retreating as climate rocks between ice age and hothouse. Throughout all these changes, the night side remains a nearly unbroken black, and the day side continents are the stark, dull gray of bare rock. After 4 billion lonely years, a green fringe first edges over the land, and the night starts to sparkle with occasional forest fires. Still, for the longest time, the unlit hemisphere remains as black as the starry space surrounding it, the dark interrupted only by these fleeting fires and by occasional flash of lightning or splash of aurora. Until, very recently, in the last few hundred years, just a twitch in the life of the planet. Whoa, what is this? Something new. Suddenly, the planet lights up in a peculiar spidering pattern that seems to reflect an organic process, but something else as well, something cognitive. Starting in a few isolated river valleys and coastal areas, glowing points appear, abruptly dotting the night, then stitching together and spreading along widening and brightening webs, hugging the shores and eventually growing in loose nodal patterns across the interiors of the lands. On the day side, a mesh of dark lines becomes visible, winding between the locations of those night lights, each swiftly surrounded by a growing verdant grid of novel angular geometry. Soon, regular movements of small wave-generating objects start crossing the oceans, and bright linear clouds start streaking the skies. At the same time, a host of other accelerating changes are observable in the atmosphere, the land, the oceans, and the ice. Finally, just 60 years ago, a blink-and-you-missed-it interval in this fast-forward view, began the curious anti-accretion, with small bits of Earth stuff jumping into space, little insect-like constructions of refined metal, bristling with sensors, thrusters, and radio antennae, started leaping off the planet, sallying first to the nearest worlds and then to those farther afield, sending pictures and other information home to their inquisitive builders, signaling the arrival on Earth of curiosity and gravity-defying technology. Yes, after billions of years of geology as usual, something new and strange is definitely happening here. What is the meaning of these new changes? And then I tell you, in the next 100 pages or so, I trace the history of the Earth, again with a focus on the major transitions in order to be able to put the transition that's happening now into context. Because it's interesting, if you look at the history of the planet, one thing you quickly learn is, as I said in the intro, that we are not the first species to come along and mess up the planet. It's been done before. In fact, 2.5 billion years ago, these little guys, the cyanobacteria, discovered a new source of energy. And they exploited that energy source so widely and globally that they polluted the entire atmosphere with a dangerous gas that led to a drastic climate change and caused the extinction of many, many species. Sound familiar? Well, what these guys, the cyanobacteria, discovered was solar energy. And they perfected photosynthesis. And they spread around the globe very successfully, using solar energy to break apart carbon dioxide and water and make organic stuff for food and fuel, and spitting out this waste gas, O2, oxygen. And they filled the atmosphere eventually with oxygen. And the thing about oxygen is it's poison for organic life. And that may sound like a strange thing to say because we love oxygen. I mean, personally, I know I do. Yeah, good stuff. But that's because, of course, we've evolved to exploit this chemical property of oxygen that it reacts strongly with organic matter. Before that ability to evolve, to do that, I mean, we call that respiration, and in every one of your cells is full of these little power plants that use those reactions to power. That's how we live, that's how we get energy. But when oxygen reacts with organic matter, it does react powerfully, and before life had evolved to take advantage of that, when the oxygen first appeared, it was disastrous. It caused many species to go extinct, and it probably caused a huge climate disaster by reacting with the methane in the atmosphere that at that point was keeping the Earth warm, leading to what we call the Paleoproterozoic snowball Earth, when the Earth was completely frozen over and life might have nearly gone completely extinct. This is all by way of saying that it's not a new thing for a species to drastically change the planet. But obviously something new is going on here. I mean, we don't hear this story and go, well, those cyanobacteria, they were just so irresponsible. How could they? No, we don't say that because they're bacteria, right? And we don't say what were they thinking because they don't think, they're bacteria. But when we see ourselves doing something that seems analogous, then of course those of us who are paying attention, we do feel a great sense of responsibility and concern. So what is the difference? In an effort to refine this question, I categorized all the different kinds of catastrophic changes that can happen to planets. And I basically decided there are 4 kinds of planetary change, 4 kinds of catastrophe, categorized with respect to the role of life. I will very quickly lead you through these 4 kinds of planetary change, if I can get the projector to stop going off. There it goes. So the first one is what I just call random catastrophes. An asteroid hits and wipes out the dinosaurs, or this has happened many times. Or there's a big burst of volcanism because of some fluctuation in the interior convection of the Earth. That's also happened many times. The greatest mass extinction ever, 250 million years ago, the Great Dying, when 90% of species were wiped out, was mostly because of a big outpouring of volcanic material from a little burp in the interior of the Earth, little switch of the convection. So these are catastrophes where life has nothing to do with it. Life is an innocent bystander in the wrong place at the wrong time. The second kind of planetary change, what I call biological catastrophes, this is when the evolution of life itself leads to drastic changes in the planetary environment that cause other species to go extinct. Some species are just so successful that they change the environment to the detriment of others. And I used the example already of photosynthesis, which is why I have the leaf here symbolizing this. There are other examples in Earth history of this kind of change as well. What I call planetary change of the third kind is inadvertent catastrophe. And this is largely what's happening now. This is, gosh, why does that keep going off? It's keeping me on my toes, that's all. This is what happens when you have a very clever species that invents technology and begins to modify its local environments very successfully, allowing it to spread farther and farther around the planet, inhabiting more environments than it may have initially been able to through this technological modification. And it's so successful at doing this, they're so successful that unbeknownst to themselves, they begin to change the global environment, at first having no idea they are doing so. And this I have symbolized by traffic because, I don't know why it's doing that. I'll just keep my finger on the thing here. No, it doesn't really matter. Each of these cars is being driven by somebody with agency, right? I mean, they can see obstacles coming and steer around them. They step on the brake if they're about to hit something. They're in control of their vehicle. And yet you can look at the system as a whole, at the global transportation system, and ask, well, who's driving this? And the answer is nobody, right? there's not really anybody driving the system. Do you know why that keeps cutting out? See, when I touch the cursor, it then comes back on. Could be the power. Maybe that's it. Maybe it is maybe it thinks it needs to be in power saving mode.
It's just the setting of your screen light.
Huh. Well, anyways. Well, maybe what we just did will fix it. Everybody cross their fingers. Anyways, it's not a big deal. It's just a little distracting. So as I was saying, each of these cars is driven by a person with agency, but you can ask who's driving the entire system, and the answer is kind of nobody. It's just sort of happening as if sort of unconsciously. And this is what I call the Anthropocene dilemma. It's where your sphere of influence exceeds your sphere of awareness. Cognitively, it's similar to, think of a child who has not yet developed situational awareness and is sort of knocking into things and doing what one does when one hasn't become fully aware of one's influence. And when you think of it that way, you realize that in some sense the challenge of humanity in terms of sort of systems analysis and cognitive development is really rather simple. It's like a child sort of learning not to soil their crib. That's what we collectively, globally need to do. It may, in a certain sense, not be that hard. Nonetheless, this is our current challenge, and this is what I call the Anthropocene dilemma. And there are several examples of this kind of inadvertent change. There's obviously the rise of CO2 recently, what we call the Keeling curve. Technology is not always our friend. This one's work. Doesn't really matter. I'll just step over here. The rise over the years of CO2, you've seen this curve before, but this is a few years out of date. It says 395 parts per million now. Of course, now it's over 400 parts per million. And this is an animation from the California Academy of Sciences that shows the sources of CO2 in the industrialized cities mostly. And if you look at this carefully, you can see the sinks of CO2 where it's ending up are the largely forested areas. So there's actually a lot of information here. And then there are famously all of the effects of this rise of CO2 that we've heard so much about, the decrease in sea ice over the years. And you've heard a lot about this, and I'm not going to belabor. I don't think anybody here would doubt that this is an inadvertent change of the third kind. Another good example of this is ozone, the ozone depletion, which here you can see the ozone hole in the 1970s. We detected it. It got deeper in the 80s and into the 90s, and then sort of started leveling out and even decreasing a little bit in the year 2000. This was clearly another one of these inadvertent catastrophes. The chlorofluorocarbons, these chemicals that were causing this, were introduced as new refrigerants that were safe and non-toxic and environmentally friendly. And indeed they were. They were improvements over what we had been using previously, these stinky chemicals like ammonia, really nasty stuff. And they were non-toxic and safe. Here in the troposphere where we live, they don't react with anything. The invention of these chemicals was very clever, but it wasn't quite clever enough, because we can never think of all the unintended consequences of introducing something new into the environment. And when these CFCs, these chlorofluorocarbons, start leaking up into the stratosphere, where there's a lot of ultraviolet light, then something different happens. Some of those ultraviolet photons nick off some of the chlorines from the chlorofluorocarbons, and those naked chlorines are very reactive with ozone, and that was the problem. A problem we discovered, by the way, because we were exploring the planet Venus. And some chemists just out of curiosity, we're trying to understand why there wasn't more oxygen compounds in the upper atmosphere of Venus, and they figured out that it was chlorine that was destroying oxygen in the upper atmosphere of Venus. And then some other scientists read that paper and said, oh, wait a minute, and made the connection to Earth and sounded the alarm. So it was a good example of how just this curiosity-driven exploration of the solar system sometimes gives us very practical, necessary information to do a better job on our own planet. But anyways, what happened then, I think, was instructive. The scientists sounded the alarm. There was a global conversation about this, more like a global argument. People said it was a hoax. The companies that were making a profit off of the CFCs hired scientists to put out, fake science, saying that it was a hoax. There was denial, all the same dynamics we see at play now in the climate change debate. But in this case, the truth won out. It became undeniably true that this was a danger to one of the basic life support systems of our planet. And there were global agreements made, most notably the Montreal Protocol for the regulation of ozone-destroying substances. And the companies that were making the CFCs phased them out, not because they suddenly decided that they were going to abandon the profit motive, but they realized they could make a profit in introducing in manufacturing the replacement chemicals, and at least they could still make a profit. People still wanted to use refrigerants, but in a way that was not destroying the ability of our planet to protect us from solar radiation. So this is a success story, and it is an example. It's the first example I want to offer of the next kind of planetary change, which is planetary changes of the fourth kind, intentional changes, where there is a global response to a global problem. And ozone is obviously a success story in that light. It's not that this is easy. There are some ways in which ozone was a much easier problem to solve than, say, climate change. But nonetheless, it serves as proof of concept that we are capable of this kind of a response, that we have it within us to have a different kind of relationship to the planet and to the systems that we depend upon to live. Other examples of intentional change, obviously, there's the most pressingly, this is going to come back on a second after this, yeah. Most pressingly, there's the need to change our energy system because of the threat to the climate, because of our carbon dioxide emissions. That is a change that is happening, inevitably will happen. It's just a question of how fast it will happen and what level of damage it will do getting from here to there. 100 years from now, we won't be using fossil fuels. We'll have a new energy system, a global energy system, even if we are as dumb as we could possibly be and dig up every gram of reduced carbon there is and burn it all. We still won't be using fossil fuels in 100 years because there won't be any. So we are making this transition. It's just a question of how fast we can do it and how much damage we'll do along the way. I think 100 years from now, we'll look back at our energy system now and think, how could we? That was ridiculous and it wasn't that hard. And I think at that point, we'll be in the process of repairing the damage and pulling CO2 out of the atmosphere. But this is our biggest challenge right now, but it doesn't end there. If we're going to think of ourselves as long-term actors on this planet, and one of my big arguments is that we need to stop thinking of ourselves as just thinking of the short term. We need to think multi-generationally. We need to think of ourselves as collaborators with our descendants and our ancestors, and part of a multi-generational process and part of a global process. And when we start thinking that way, you become aware of some longer-term threats to the well-being, not just of ourselves, but of the biosphere, that we have the possibility of preventing and of averting. And then once we have that possibility, I think inescapably it means we have the responsibility. I mentioned before the impact of the asteroid that did in the dinosaurs. Well, That's not a singular event. If you go to a longer time scale, Earth has been hit multiple times and will be again. I have a little animation here from the California Academy of Sciences. This shows these are the orbits of Mercury, Venus, Earth, and Mars. And each one of these little insect-like things, this is real data. Each one of these is the orbit of a known Earth-crossing asteroid. These are all objects that eventually could someday hit the Earth. And those are all the known ones. There are more out there that we haven't detected yet. So this is all by way of saying that there's a lot of stuff in the solar system that is still out there to hit planets. And eventually, Earth will get hit again. Now, this is not something you should lose sleep over tonight or this year or next year. There are other things I might suggest if you want to lose sleep, but we can talk about that later. But it's inescapably something we'll have to deal with if we're going to be around on the time scale of centuries and thousands of years. And it's also something that won't be that hard for us to prevent. The good news is if one of these is heading towards Earth, we'll see it years, probably decades in advance. And it's not that hard. It wouldn't be that hard for us to avert. You don't have to send Bruce Willis up and nuke it, even though that makes maybe a fun, maybe not, maybe a dumb movie plot. But that's what they do in Hollywood. But that's actually a really bad thing to do, because then you have a radioactive cloud of debris heading towards Earth. No, all you have to do is go up and give it a little nudge. Just push its orbit a little bit. Get it to miss Earth by 10 minutes. It's not like as, the macho solution. It's the more gentle, just give it a little push solution. But that turns out to actually be the better way to deal with it. So in the long run, this is maybe the first time in planetary history, the entire history of the planet, the entire 4.5 billion years history of the planet, Earth has been vulnerable to these impacts until now. So maybe that part of this Anthropocene transition is this is the beginning of the time when Earth's biosphere is no longer needs to be terrorized by these kinds of events. Another one of these longer-term considerations that, again, I think ultimately becomes our responsibility if we discharge our shorter-term responsibilities, has to do with climate. We are under the illusion that left to its own devices, the Earth's climate is a paradise and Earth is benign and everything is fine if we just leave it alone. That is an illusion, because our civilization has come along in this 10,000-year lull, this time of relatively warm and stable climate that is very unusual in Earth history and won't last. So if we wait long enough, there will be another ice age left to its own devices, and our civilization would not survive that. Not only that, but a lot of other species would be driven to extinction by that. Ice ages cause mass extinctions. So the good news is that this would be easy, again, for us to avert. We've already shown that we're capable of inadvertently causing big climate changes to the planet. If we get a handle on that behavior, which I don't think we have a choice, if we're around long enough to worry about this problem of the ice ages, it will only be because we have gotten a handle on this inadvertent messing with the climate. And once we get to that point, we'll know enough so that it wouldn't be that hard to tweak climate just a little bit to prevent it from going into one of these disastrous phases. So I think it's uncomfortable to think of ourselves in this role of sort of managing the planet, but I think that it's kind of unavoidable. I think the same skills and responsibilities that we have to call upon to deal with the immediate threat of our self-induced climate change, when we extrapolate those into the future, we're left sort of holding the bag of this planet with the responsibility to learn how to manage ourselves and manage the planet better. I want to wrap up so we have some time for discussion. The last part of the book that I won't really go into now, I get into a little bit the question of the search for extraterrestrial intelligence. And the reason why I do that in a book about humans on Earth is because it's a way of abstracting the question of what does it mean for planet-changing technology to become part of the way a planet functions, and what does it mean for societies to potentially live for geological lifespans. And the theory of SETI turns out to all be about the question of longevity of civilizations. If there is anybody out there, it's because civilizations can last longer than we've lasted here so far, much longer. And people have done the math of SETI, and it turns out the central question of SETI is the same as the central question that we face now, which is it possible for a species, a civilization with planet-changing technology to evolve a long-term, healthy, stable relationship with a biosphere? And so by looking at SETI, it's a way of sort of abstracting that question beyond just the specific example of what's happening on Earth, but also I think then we can turn the telescope around, and that perspective hopefully sheds some light on the problems we're facing here. That's what I tried to do in the book. And I talk a little bit about the very long-term history, the eons of Earth history. There have been 4 so far. The Hadean, when Earth was hell, couldn't have any life, just all impacts and steam and volcanoes. The Archean, which was the time of the first life. The Proterozoic, which was the time when the eon when life took over the planet, when that oxygen catastrophe I mentioned happened. And when it flashes on quickly, I'll show you this is when life took over the planet with that oxygen catastrophe. And the Phanerozoic is when plants and animals, when big life, multicellular life happened. And that's supposedly the eon we're in now, the Phanerozoic. But I talk about the possibility that this boundary we're at now, this transition, might be not just the beginning of a new little epoch, which happens all the time every few million years, but we could be at the beginning of a new eon that I call the Sapiezoic eon. That is, if cognitive processes, if intelligence, technological intelligence is really going to become a lasting part of the way the planet functions, then it's a much more profound transition. It's not just another epoch. These are all major transitions in the relationship between life and the planet. There have been sort of 4 different planets. And I'm suggesting that maybe we're beginning the 5th eon now, the Sapiezoic, the time of wisdom. It's an aspirational term, but in other words, if this is going to last for a geologically significant length of time, it will only be because we've got our act together. So it would have to be an age of wisdom if it is to persist. So if it is going to be an eon, it will be the Sapiezoic eon. All right, so I want to just close by reading you a little bit from near the very end of the book. So after Monkey with the World, I talk about Terra Sapiens, or I go into a little more detail in my vision of what it would mean to have this different kind of relationship with the planetary environment dominated by these intentional changes of the 4th kind, a wisely managed planet. Then I talk about SETI. And then at the very end, the last chapter is called Embracing the Human Planet. And I talk a little bit more about this history we have that I alluded to at the beginning of responding to climate change. And I trace a little bit of the evolution of our species and show how a lot of the big innovations that led to modern humanity came about due to existential threats caused by climate change. 190,000 years ago, there was this genetic bottleneck where the number of human beings may have been reduced to as little as 1,000 or fewer survivors, and we repopulated from that small population, which, by the way, is why humans are so genetically undiverse compared to other large mammals. We're very, very similar, all of us, because we survived that bottleneck, and we survived it by reinventing ourselves socially and technologically. So we've done this before, this reinvention that we need now. And in this chapter, there's a section I end with a sort of taxonomy of pessimism and optimism. There's a section about pessimism that I call the power of negative thinking. And I warn against the sort of toxic, reflexive assumption that we're doomed, which I think is easy to see how people reach that conclusion, but I conclude it's also based on a sort of extrapolation based on not that much information and ignoring our deeper history. After all, for a long time we were hunter-gatherers. Imagine a hunter-gatherer trying to picture a modern city, trying to explain to them a modern city. Maybe that's as difficult as it is for us to imagine this far future Earth where we've achieved a sustainable way of living. We have reinvented ourselves many times. And of course, when modern cities were first invented, they were horrible places to live because we didn't know how to do it well. And then one big invention that changed that was the sewer system. We used to just throw our shit into the streets. Now we have sources. We take them for granted. They're underneath. They're hidden, but they make cities livable. And the way I think about it is that now what we need to do is invent the sewer systems of the 21st century, because we're not throwing our shit into the streets anymore. We're throwing it into the air. And we need the innovation, just as we had innovations that allowed us to live in cities. Not that our cities are perfect, but they're a lot better than they once were. They're not public health disasters. Now we need the innovations that will allow, both social and technological, that will allow us to live well as a global civilization. So anyways, I'm going to end with the very end of the book where I talk about optimism. And I'm going to read you a little bit. I'm going to read you almost the very end of the book. I'm not going to read the last 2 paragraphs because I don't want you to know how it ends. All right. Right now, the subject of the future is rife with anxiety. Visions of apocalypse dance in our heads. The topic of the Anthropocene is often associated with doom and gloom, with an "is the earth fucked" mentality. This is understandable, but it's not the whole story. Let's not dwell on these prophecies to the point where they become self-fulfilling. I propose that, on the contrary, the true Anthropocene is something that should be welcomed. Though it is yet only in its infancy, it can be glimpsed. Don't fear it. Learn to shape it. It is the awareness of ourselves as geological change agents that, once propagated and integrated, will provide us with the capacity to avoid doom and take our future into our own hands. Understandably, we are uncomfortable with our role as reluctant planetary engineers. Discomfort sometimes manifests as self-loathing and denial. But this is our task, and we can't afford to wallow. It's time to human up. We have to stand and face it, get up on our big bipedal frames and look in the mirror. Wake up and find out that we are the eyes of the world. Earlier in this chapter, I described flavors of pessimism. There are flavors of optimism, too. There's cosmic optimism stemming from a belief that the universe in its vastness bends toward life and intelligence, and that what happens here doesn't really matter anyway because there's plenty more where we come from. There's data-driven and historically based optimism, which focuses on positive indicators, of which there are many. Poverty, malnutrition, and infant mortality are in retreat globally. Levels of education are on the rise. Communication continues to become cheaper and easier. Population is plausibly heading towards stability. Solar and wind energy are getting cheaper and will continue to do so. These are all trends toward human freedom and environmental sustainability. There's pragmatic optimism. We really don't know what is going to happen, so why not spread hope and encourage engagement? Exponential technological innovation is transforming our world in surprising and accelerating ways. Possibilities that until recently seemed magical are now imminent, rendering the future frightening and exhilarating, but above all, unpredictable. Where there is uncertainty, there is also hope and choice and room for faith in ourselves. I believe we're just getting started on this planet. Nobody knows the odds of our being able to navigate the evolutionary obstacles before us, but there is a real hope, and it is this: that our evolving technological capacities can allow us to maximize our innate social prowess. equipping us to meet the novel threats we have accidentally created and to become something new in the process. We have done this before.
Thank you for a very provocative and illuminating talk, all of which he did without ever using a verbal weed like duh. It's very, very impressive. We're going to take a few questions. It can't be too long because some of you have to go. We'll start with the psychiatrist.
Well, love the metaphor of a wise mind creating a wise earth. But unfortunately, you came up with wonderful ways to deal with almost impossible problems, except for the nuclear destruction that's most likely to be the immediate short-term problem that humans could have. Do you think we're wise enough to figure out a way around that?
Yeah, that's a tough one. Of course, I grew up in the shadow of the bomb, and that was the big worry. And when I was in college, I went to Brown University and helped form the Brown Disarmament Group, and went and protested at the nuclear test site. And then it seemed as though the Cold War ended, and we were disarming, and that was good. And it seemed as though we can relax, except for. I wish we had more completely disarmed when we seemed to have that window. And yes, this is something that I'm very worried about, and it is a credible threat. And of course, I don't have any magic bullet. Now, it's horrible to contemplate. If there was a nuclear war and a nuclear winter, it wouldn't necessarily be the end of the Anthropocene. It might be 1,000 years or several thousand-year interregnum, and it, and it's. I'm not saying, that means it's fine. I don't think that at all. But, well, I'm saying that it geologically, it might still look very similar 100 million years from now. That there was this little pulse, and then there was this pause, and then things happened again, right? So from a certain point of view, I mean, obviously, I personally am very concerned about that, and am committed to try to do what sometimes seems very little that I can, but to do what I can to educate and prevent that. But it is sort of detaching ourselves for a second philosophically and thinking about it geologically. I'm not even sure that really changes the picture that much, because it would not lead to there's no plausible scenario in which nuclear war leads to the extinction of the human race. It just leads to the destruction of our current civilization. And what comes after is the subject of a lot of science fiction, some of which is good, a lot of which isn't.
Young lady right here.
Could you talk a little bit about what we're doing now to cause climate change, or what we're doing, intentionally weather change, and also as a weapon, and also aren't there shooting some things in the sky to combat the warming of the climate?
I think you're talking about geoengineering. And there are these schemes proposed that you could do what they call solar radiation management, squirt a whole lot of aerosols, sulfur dioxide particles, probably how you would do it, into the stratosphere, simulating what happens in the aftermath of a big volcanic eruption, in fact, which cools the Earth a little bit. There are schemes like this that are proposed. Nobody's doing it on any large scale. It's pretty controversial. In my view, it's not a smart thing to contemplate right now, even though I've said in the long run we will probably want to manage climate in some way. We're far too ignorant right now to try something like that without all kinds of unintended consequences. Sure, we know enough to to cool the Earth a little bit on average, but what would that do to global precipitation patterns? Would it cancel the monsoon somewhere where it would lead to famine and drought? We're playing with fire if we do that because we just don't know enough yet. So there's no magic bullet that releases us from the great responsibility to simply reduce our carbon emissions. In the long run, I do think there will be technological fixes, and like I said, 100 years from now, I think we'll probably be pulling CO2 out of the atmosphere and repairing some of the damage. But I think it's very foolish to advocate trying to find some quick technological fix. Even if you could do that solar radiation management and lower the global warming effect of CO2, you would still be causing ocean acidification with all that CO2. So there's no way around our great need to lower our effluence of CO2 and get that 400 parts per million down ultimately to a safer level.
Gentleman right here.
What's your next project?
Next project. So thank you. I'm halfway through. So the book side of me is about half of me, and for that I'm halfway through another book that I'm co-authoring with a guy named Alan Stern, who is the principal investigator of the Pluto mission, the New Horizons mission that flew by Pluto recently and is now on its way to one more place before it shoots out of the solar system forever. And he and I are co-authoring a book about the history of this mission, which is sort of rather extraordinary. It starts with a bunch of graduate students in 1989 who got this crazy idea to send a spacecraft to Pluto. And we're told they were crazy and didn't give up. And now the same gang are mid-career and older scientists who have just successfully flown a mission to Pluto 25 years later. So it's their story, basically. So I'm co-authoring that with the guy who did it. And then the other half of me, the science part of me, I'm working on a number of space projects. There's a Japanese Venus orbiter called Akatsuki, which is in orbit now, and I'm a participating scientist on that mission and doing a few NASA projects, trying to get a new NASA Venus mission, although that's often like Charlie Brown kicking the football and ending up on the ground, looking up and wondering what happened, or so, and then getting up and kicking again. So I'm undergoing that process with another mission. So yeah.
Very exciting. Norman?
Being an amateur philosopher, I view theology as being in the interstices of science. And not having another planet with human beings comparable to ourselves, seems to me that the plausible explanation for life and existence is theology rather than science. Would you care to comment?
Yeah, sure. I also am very interested in theology. In fact, I just got back from a really interesting meeting in Stellenbosch, South Africa, 2 weeks ago, which was a bunch of theologists and scientists. And the theme of the meeting was questioning our assumptions. And they had everybody from whatever discipline you were from get up and say what the assumptions of your discipline were, and then question them publicly. So it was really fun. And I think I agree with you that theology exists in the interstices of science. But I don't know that one would have to say that the existence of human beings is more a question of theology than of science. I think it's one that you can look at meaningfully through both lenses. I don't really see that as a dichotomy. I mean, we can come up with very interesting scientific explanations for why we're here. We can understand the formation of the Earth out of its out of the materials that predated it. We can understand, to some extent, the origin of life on the young Earth, although we're still trying to piece that together. We can understand the evolutionary processes that led to complex life and cognitive life and all that. So those are scientific ways of looking at, that I think are valid, of looking at what we're doing here. But then the question remains, of course, why, and why here and not somewhere else, and what's the purpose of all this, and those are questions that you could say are beyond science. I don't think that theology necessarily has answers to those questions either, but they certainly have, interest. I've learned of many interesting approaches to those questions, and so I think those are valid avenues. So I don't personally see it as an either or. I think that both of those areas of thought can lend a hand in our trying to understand our existence here.
We'll just take a few more questions. This young man here.
Yeah, like a few days ago, there was an mention in the news about fossils found in Quebec, signifying like earlier signs of life. Was that like before the cyanobacteria, or?
Yes, I just learned about that myself. The gentleman's referring to this report of some of the earliest evidence of life on Earth. And yes, it was definitely before the cyanobacteria. The cyanobacteria, that was about 2.5 billion years ago. Life had already been around for a while, and what was significant about that was the use of solar energy and the changing of the atmosphere and sort of life becoming this global chemical disturbance. But that was clearly after life had existed for a while, and those were very sophisticated organisms, chemically sophisticated. And the question of when life first started is still something we're investigating. We have pretty good evidence back to about 3.5, and some people think 3.8 billion years ago, although that 3.8 is controversial. And this report that just came out that you're referring to potentially is 4 billion year old fossil life, which would be, if it's validated, the oldest sign of life on Earth. And it's very interesting if we can push it back that far, because that's right about the time when Earth probably became habitable. Because if you go back before 4 billion years, then you're in this period of time when Earth was just being bombarded all the time from space by these impacts. We can tell from the surface of the moon that there was a time when those were just happening all the time, and then it sort of leveled out. And we imagine at that point the surface of the Earth became a little more stable and friendly, and there were oceans and places where things could evolve. And that phase seems to have started around 4 billion years ago. So if this is right, if this result proves to be correct, if it's valid, then that means that life happened very quickly as soon as there were conditions that would allow it to happen. And that's very interesting as far as, it's interesting as far as what happened on Earth, but it also has hints about extraterrestrial life, because it implies that once you have the right conditions, that life can form pretty easily and pretty quickly. So if anything, life that early on Earth seems to point towards it not being that hard a thing for a planet to do, given the right conditions. But I think that result will be controversial for a while, and that's as it should be. That's the way, when somebody comes up with a result that seems to change the story, then scientists all attack it. Not because we're mean, some of us are, but because that's how science works. It's like, then somebody else will try to get a paper published saying what's wrong with that paper, and then, which they surely will, but then if it survives the attacks to come and proves to be valid, then that will be a very significant finding.
The young lady in green sweater.
Has our study of extremophiles expanded our understanding of life enough for us to detect life forms on Venus or Titan under the surface of Mars, possibly Europa? And if so, are there any missions in the works that NASA to test that theory?
Great question. So she's referring to extremophiles, which is the name we give to all these discoveries in the last couple of decades. That literally means the lovers of extremes. That we've discovered, there have been a series of discoveries of life that lives in different kinds of environments that we previously thought were uninhabitable. Life that lives at very high temperatures in very acid-rich waters, at very high pressures, inside of frozen rocks. All these discoveries sort of push the boundaries of what we thought were the sort of habitable boundaries. It's a wider box now in all these different conditions. This is one of the developments that has led to the burgeoning of astrobiology as a field where we think we might really be able to find extraterrestrial life, because a series of discoveries have been made about other planets and about life on Earth, both of which encourage this idea that it might not be that outlandish to find extraterrestrial life. And yes, it does encourage us to think of, for instance, life in the ocean that we now know is underneath the ice of Europa. Jupiter's moon, Europa, probably has the largest ocean of liquid water in the solar system, not on Earth, but on Europa. And even other more exotic places. You mentioned Venus. Well, the surface of Venus is, I mentioned, is a sweltering oven where you wouldn't expect to find life. But in the clouds of Venus, there's actually potentially a habitable zone. It's roughly this temperature and pressure, and there is water. It's in a bath of concentrated sulfuric acid in those clouds, which we used to think would mean it was completely uninhabitable, but now we've learned of life on Earth that lives in conditions more acidic than the clouds of Venus. So maybe there's something living in those clouds. Our range of possible environments where we've realized there could be life has become larger. And so your question, are there missions planned? Well, yes, we have a mission now in the works to go to Europa, probably to launch in 2023, I think, and then take several more years to get there. But then it's going to be a Jupiter orbiter that makes several close passes by Europa, and I believe it's going to have a lander that actually goes and lands on the ice. So it won't go down into the ocean, but if there is something interesting happening with organic evolution in that ocean, we think there'll be clues in the ice itself. So that's something, and there's also a mission proposed to go to Titan, and possibly to Enceladus. These are both moons of Saturn, Titan and Enceladus, where we think now there could potentially be possibilities for life. The Venus, I'm involved, as I mentioned, in proposing some missions where we're trying to get one funded. So the only one that's really in the works that speaks to your question right now is, well, there's a series of Mars missions, of course. In my view, Mars is not the best place to look for life. It's maybe the best place to look for fossil life, and we're doing that, and that would be really, of course, amazing to find. But as far as something alive today, I think Europa, Titan, Enceladus, maybe even Venus are better bets. And
New Jersey?
And, well, New Jersey depends on what exit. But so we're doing some of that, and the rest of it, a lot of us would like to, but of course funds are limited, so we kind of have to do one mission at a time. So get in line, you know.
I'm going to end with two more, Bernard and then this young man over here. And then we'll have to stop because it's getting late, and you can all come over to David, and he'll be inscribing books, and you can ask him further stuff. Go ahead, Bernard.
Teams of astronauts go out, and Team A finds a planet in which there's an ocean full of DNA and RNA and protein, but no membranes and no cells. And Team B finds a planet in which there are lots of robots made out of transistors and electric motors and things like that learn to speak English and explain that as far as they know, they're robots all the way back. So the teams come back, and each one claims to have discovered life and says that the other team didn't. Does one of these teams win the argument?
What a nice way to ask the question, what is life? Which is a central question of astrobiology. And of course, we don't know the answer. It's a paradox because we have to have provisional answers in order to search. We can't really say what life is because we have one example of life here on Earth. Even though we have all this biodiversity, it's all related. And so we really only have one biosphere. And scientifically, how can you define something well when you have one example of a category? So we won't really be able to define it until we have many examples. So we have to search for it. But how do you search for something that you don't have a definition of? So it's a little paradoxical. So we search with provisional definitions. And our provisional definitions would say probably that neither of those groups had found life. And that would probably be wrong because there's a way in which I think they've both found life. You know, I mean, there's a whole other talk, what is life and the different definitions of it. But often we say it's a self-perpetuating chemical process bound by membranes and reproducing according to Darwinian evolution. That's, it's not a great definition because, like I said, we don't really have the knowledge we need to come up with a good definition. So to me, it sounds as though both your groups of astronauts found life. If there's if there's a world where DNA is reproducing itself with the help of proteins, then as far as I'm concerned, that's life. And it may well be, and I think you know this because you phrased the question in a knowing way, it may well be that life on Earth went through a phase like that before it was, some people think before life was cellular, there was just sort of a bath of chemicals that was behaving that way in an ocean or in a pond somewhere, and then cells developed, but we don't really know. The robots, I'm going to say if they're self-reproducing robots, and if they are, they're probably going through some Darwinian process where the ones that are better at reproducing themselves reproduce themselves and evolve, then I'm going to say that both of your groups of astronauts have found life. And I think that they'll continue to argue about it, and nobody will be satisfied with with the results of that argument.
I might add, Bernard, there's a new book out called Homo Deus by Yuval Noah Harari that addresses the future of robotic life on Earth and speaks to many of the things he was alluding to. That is very interesting. Anyway, this young man.
My question is in regards to how we can achieve what you've called for, a better understanding of deep time and sort of a space situational awareness where it's a planetary perspective. And we know that for astronauts have been able to achieve this just by going into orbit, and we have through film or through some planetary programs or planetarium programs where we can sort of get a snippet of the feeling of understanding deep space or time. And so my question is, in your experience in outreach and working in astronomy outreach, are there programs out there or efforts out there to really address this? Because it seems that it needs more than just a 20-minute planetarium show where it takes hours, where you're immersed in this virtual environment that you can only really achieve through our visual technology, because it's something that you cannot experience directly. So we need to use our storytelling experience and our media experience to achieve this. So do you know of any efforts out there to really address this seriously?
Yeah, I mean, it's a great question. What you're describing is what's been sometimes referred to as the overview effect that astronauts experience when you perceive the Earth from space. It leads to a lot of astronauts have reported this very profound appreciation of the sort of unity of the planet and unity of humanity. And one of the astronauts, there's this quote from one of the Apollo astronauts saying he wished he could take all the world leaders up there and have them say, like, look, you son of a bitch, look at this, what are you guys fighting over, And a lot of people who've had that space perspective have reported the overview effect and that it's very powerful. And in my view, and this also harkens back to Fred Hoyle said in the 1940s, once a view of the Earth whole from space is available to be seen by everyone, then that will change us profoundly. And I think Fred was right, and that it did, and that that Earthrise picture from Apollo is so iconic. And I think it has changed us, and it is changing us. I mean, just that realization that we live on a planet because you have not only you've been told that conceptually in school, but you've had that visual impression. Most of us haven't been up into space, but just we've seen that. And even just, you watch the you watch the weather report on TV, and we sort of take for granted now those satellite images of it, that's what a storm is this thing with arms that sweeps up against the coast. Whereas, in 1900, when the Galveston hurricane hit, nobody knew it was coming, and it was the worst natural disaster ever. 8,000 people at least drowned. These days that wouldn't be a big deal because we'd see it coming weeks in advance, and people could batten down the hatches and leave, you know. So that change in perspective of having those orbital views of, I think, is changing us. It's really just been a generation or maybe 1.5 generations that has lived with that knowledge. And I feel as though it is sort of percolating in and is affecting us and slowly helping turn us into Homo cosmicus. Now, as to your question, can we accelerate that, and do I know of programs? Well, I certainly do know of programs that people do in planetariums, like my buddy Carter Emmert over here at the, you know Carter, over at, okay, over at the Rose. You know, what Carter does, he does these amazing cosmic zoom, immersive planetarium programs where you sit there and you experience the whole universe coming down to Earth and out again, and I mean, it's very powerful. And I've done similar things. I worked for many years at the Science Museum in Denver with the planetarium there. The problem is, of course, these are the elite urban dwellers, of which we hear about so much recently, that have access to facilities like that. But there are programs now more and more. In fact, our Denver planetarium and a lot of other places have these portable planetariums that are inflatable and that you can take out to a rural community and fit like 30 kids inside of and do that same amazing immersive visualization. So I don't think that's the whole answer. I don't think you need to get everybody in the world into a planetarium and like say, hey, look at this, become enlightened. But it doesn't hurt. I think that's one way we chip away at this. I mean, in my view, just scientists out there talking and sharing what we know, the truth of our world promotes the worldview that we need. You don't have to make anything up. When you look at our world the way we actually see it, when we see it from space with Earth-observing satellites, you, of course, don't see the national borders. We are embedded in a series of processes that are global in extent, a series of cycles that are global in extent, and processes that outlive our individual lives. That's the truth of the world that we inhabit. And so I think just going out there and communicating about it in every way we can does, science is, I'm getting ready for the science march here. I think scientific truth is in itself actually very subversive of those modes of thought that we need to rail against, that limit us to thinking locally and short time scale. We inherently think on wider spatial and temporal scales when we see the world the way it really is.
I want to thank David for this brilliant and generous talk tonight. Certainly, this is what we mean by a great thinker. Do come hear Shelley Glashow in April, Nobel laureate in physics, who has also some provocative stuff to say. Meanwhile, have some refreshments, and David will be happy to sign books. Please come and have a book inscribed, and then after you do, he will be happy to answer a question.